The Pathfinder is one of the new tools incorporated in OpenDSS-G. This tool can be used to find the total distance and a path in between two buses within the model, which can be located anywhere. To specify the names of the buses, do we want to link or we want to check the distance in between? We can specify the name. The names are provided on a list that it itself populates if you decide to start writing the name, if you know the name. There is also a magnifier tool that will locate the bus within the GUI in case we need to check the location. Or if we don't know the name, we can just select the pick tool, the picking tool, which will allow us to select a region of interest within the model and will bring the name of the bus at that location. Once we have defined names, just click on play and that will calculate and estimate the path in between two buses. And it's going to give us all the total distance and the individual distance for all the segments in between those two buses. We can change the units for the distance. So if it's originally in miles, we can change it to kilometers, meters, feet, whatever is necessary, whatever we need. We can do the same operation for two different buses across the feeder. So no matter the topology and no matter the bus location, we're going to be able to calculate the distance. To do this, OpenDSS uses the Laplacian matrix. So the calculation should be fairly quick, fairly fast, and we should have that calculation on time when required. You can also export this table to Excel if required. When adding new elements into OpenDSS-G, sometimes we need to just go back and somehow try to recompile the model. And we can do that in OpenDSS-G with a click as well. What I'm doing here is we're checking a location in which we want to place a PV system. In this case, I'm just checking for the buses at a certain location across the model, and I'm creating a random PV system. Suppose here I'm going to create a 4.15 kV PV system, 3 megawatt, full active power. I'm going to define a daily profile. I don't have a radiance profile in this model, so I'm just going to select one of the profiles that we have already loaded. Let's suppose that those should be good for a PV system. And finally, we're going to select the bus. So I already copied the buses from a line that I picked in the model, which is located at the top of the feeder. And we're going to connect the PV systems Y connected. So let's check where the PV system is installed at this point. It's up there. So let's suppose I did the test and I want to go back to the original model. What can I do? I don't want to run everything again and have to leave OpenDSS-G and go back. I just select the Recompile tool and that will bring the model to the original features. Now, it could be also necessary sometimes when playing with yearly simulation, daily, time-based simulations, to go to a specific time instant. How can I do that? We have the timing tool in which I can specify the day, the year, the hour, the minute, and the seconds in which I want to place the simulation. In this case, I'm going to set it to hour 600, and that will take me to the day 25, hour 1. So with that, it's very easy to set up the simulation to the time instant I want. So what we're seeing right now is the voltage profile at that time instant. Also, we can bring some heat maps to show us what's the status of the system in that particular time instant. We can bring the power flow direction, we can bring the voltage level, we can bring overloads, power consumption. We can see in that time instant we are consuming 2.4 megawatts. So we can bring all that information very easily. Now let's suppose I want to start over. I want to bring back everything. And the next step will be to go to the timing options and select 0.0, which will bring the simulation back to the beginning. Since the beginning of OpenDSS-G, we have incorporated a FLISR automation tool. This automation tool will basically follow the instructions given on a CSV file for locating a fault and isolate it and try to restore the service on as many customers as possible. It's not a smart algorithm, it's just something that follows the instructions given on the file. What we have in this feeder are 5 zones, which are described by the switches, by the location of the reclosers that we have. We have placed a monitor to check each one of the zones separately. In this feeder we have one substation, we have 3 time points to other feeders to restore the service and in different zones, and we have 3 PV systems. Right now what I'm doing is I'm setting the simulation in time mode with time steps of 1 second. And I'm going to bring the FLISR automation tool. The first step will be to define what's the configuration file. It's very similar to the real-time simulation tool, but in this case, well, it also incorporates control commands. When opening the FLISR file, it will tell us first what's the normal operation of the feeder, which is which switches or circuit breakers are normally closed. The others will be open. And that's what the system is going to do when I click on the reset button. It's going to take the system to the defaults. And then on the column of the left, we're going to find the after fault state, which is the state in which all the switches will be after the fault. And then up to the right, we're going to find the new configuration that the feeder needs to adopt when a certain fault or after fault configuration is reached. The file looks like this. It's just a CSV file in which we define the after fault state and the future topology that we need to adopt. The only switches or circuit breakers that we mentioned to define a topology are the ones that will be enabled. If the other ones are not in that list, it's because they're open. We're going to load it up, and we're going to bring the system to the initial conditions. So as we can see, and I'm going to bring the icons to make it more visible. We're going to bring the substations and the ties to other feeders, PV systems, cap banks, and also we should bring the regulators, the regulator location. So now we have them all. You can see we have 4 regulators, one 3-phase at the feeder head, and we have other individuals per phase across the feeder. So now we're going to show the voltage. So at the same time, we're going to see the regulators doing their function. We're going to see the voltage heat map to see how the voltage gets regulated by the regulators. And at the same time, that action will be recorded by the monitors that we place in each one of the zones. So the simulation is moving forward, and we will see that the colors change while the regulators are taking action to take the voltages across the feeder to an acceptable range. You can see we went high, now we're regulating and getting to the correct point. Alright, so now for testing our FLISR algorithm or FLISR file, what we're going to do is we're gonna introduce a fault. And the first one is going to be 2 out of 3 phase fault to see how the system recovers. We're going to put it here in zone 2 and we're going to see what happens. So probably what's going to happen is that switch 2 and switch 1 are going to open, the others are going to remain closed. Probably you'll be able to recognize that state within the FLISR file. And that will tell us what's going to be the next topology. So first we're going to go to the fault menu and we're going to introduce the 3-phase fault in zone 2. We're going to connect everything and here we go. So the system reacts to it. We can see the voltage drop on the monitors and also in the colors of the GUI. And now the system is restored. We have restored the voltage in zones 1, 3, and 4. And after that, we can see also that the regulators connected to zones in which we have voltage are trying to do their job and they're taking the voltage to an acceptable range. Now, you can see that zone 4 is connected to zone 5, or there's a tie switch in between, but it didn't operate. It's because the tie switch that energizes zone 4 cannot hold the extra load in zone 5. So if we try to close that circuit breaker manually, we're gonna trip the recloser that gets connected to the other feeder. And let's try here. So we connect, we're off. So what we can do is isolate zone 5 and try to restore manually zone 4. And that works fine, works good. You can see where the fault was applied. And now the next step is going to be to clear the fault, restore the system to initial values, and keep going. Now let's try with a different type of fault. Let's try with something single phase. At the same time, in real time, we can see how the regulators are taking the system back to normal. And again, we can see that also in the data that's being recorded by the monitors. So the next step is going to be to introduce a single phase fault. To do that, we're going to go to the fault menu. We're going to select the single phase to ground fault. We're going to put it in zone 4, phase 3. You can see the system reacts and it's going to try to restore the voltage. And we have recovered zones 1, 2, and 3. We can see where the fault was applied. Everything seems to be working fine. Again, this is not a smart algorithm, it's just following a file. So we're going to clear everything and take it back to normal. And again, the regulators start acting and taking everything back into the reasonable range. We're going to put another fault in zone 1. This is a 2-phase to ground on phases 1 and 2. Everything opens, and now we're restoring zone 4, 2, and 3, using connections to other feeders. And everything looks fine. We can also change the heat map that we're seeing. Right now we're working with voltage to illustrate how the regulators are acting on the GUI, but also we can use isolation, which is very practical and allows us to see which zones are energized or isolated during the FLISR scheme operation. So we're gonna stop here, we're gonna clear the fault, and we're gonna try something else. In this case, it's gonna be a single phase to ground fault, and we're gonna put it in zone 5, phase 2, and we can see the system reacting to it. So now we're gonna restore zone 1, 2, 3, and 4.